Kia ora and welcome to this video on question 3 of the 2016 Scholl Calc exam. There's two parts to this. Part A is a sneaky integral problem. Part B is finding the equation of a curve from a differential equation. So both questions are set in the integration domain. Alrighty, first question. Hopefully you've had a go at this already. You may have got frustrated at it because we're given an implicit expression for this function and we're asked to find an explicit expression. Okay, if it said find an expression for f of x, we go, hey, we've already got one, but it's an implicit one. F of x is not the subject of it. And the first thing that frustrates is how can we find this integral on the right hand side when we don't know what f of x is to begin with. Okay, it seems a little bit strange to find this integral of f of x times sine of x when we don't actually know what f of x is. And the integration by parts formula says if you've got an integral of a product, f times g dash, then to work it out we need to know, okay, what f is. Well, just leave it as f of x, but we need to know what f dash is. And if we don't know what the function is, how can we find its derivative? Now what you need to realise, the catch in this, so if you haven't tried this problem, please have a go before I give it away. This whole beast here, which we're struggling to work out, is a definite integral. So what is a definite integral? You've tried the problem. It's just a number. This whole thing, and in the mark schedule they label it A. It's just a value. It's just like, it could be 2, it could be 5, it could be negative, but it's just a number. That tells us that our function is just a linear function, x minus a. Now that's not sufficient. We need to now find the value of a. But because we know it's a linear function, we can now use the integration by parts formula. Okay, so just looking at the stuff in blue, the integral between 0 and pi over 2 of f of x times sine of x. Okay, I'm going to call, what am I going to do? I want to make this right-hand integral. When you use integration by parts, you try and make the right-hand integral an easier integral to find out. So I want f dash to be something nice. So I make my f, well, I replace f of x with x minus a for a start because I know a little bit more information about f. But if I call this f, this is my g dash. So on the right hand side, the integral becomes x minus a times g, which is the antiderivative of sine, negative cos, minus the integral of f dash, which is 1, the function's x minus a, the derivative is 1, times by g, which is minus cos. And the whole thing needs to be evaluated between pi over 2 and 0, eventually. So first thing is I like to find the integral first, and then evaluate it. So I've got x minus a times negative cos, which is actually the same as writing a minus x, times cos, personal preference here, but it's a little bit tidier, plus the integral of cos, evaluated between pi over 2 and 0. Now that integral on the right hand side, the integral of cos is an easy integral, a minus x times cos plus sine between pi over 2 and 0. Let's see what happens when we sub in these limits. Cos of pi over 2 is 0, so that whole first thing disappears. Sine of pi over 2 is 1. Then we minus the integral when we sub in 0. We get cos of 0 is 1, and a times cos of 0 is a. Careful with brackets and minuses here. And then sine of 0 is 0. So we get that. Okay, so the left-hand side, we had f of x, which was equal to x minus a, and actually no, I didn't need that at all. I just remember I called this whole integral equal to a. So therefore 1 minus a, which is what the integral came out to be, is equal to a. So a must be equal to a half. Therefore the function is x plus 1/2. Let me just think about that for a sec. I think it's a little bit different to the schedule. Why is that? Because a is a half and I said x minus a. That's why. Cool. So what a simple answer for such a weird problem. Easily tricked and very hard to do integration by parts if you didn't know what the function was to begin with. You had to have that little bit of insight. Okay, part B. Curve passing through the point 1, 1 has a property that at every point on the curve, the gradient of the curve is x minus 2y. In other words, the gradient function is equal to x minus 2y. Show that the derivative, to d dx means differentiate with respect to x, e to the 2x times y, show that it equals x e to the 2x for this curve. Okay, that's a product. So to diff a product, we need to diff the first thing times by the second thing, diff the second thing, y diffs to dy dx, times the first thing, factor the e to the 2x out, turns out I can't diff properly, e to the 2x diffs to 2e to the 2x, my bad. Okay, much better. And then use the fact that dy dx is equal to x minus 2y. So we replace the dy dx bit with x minus 2y. And the 2y's cancel, and we've got x e to the 2x. So what that means is for this particular curve that satisfies that differential equation we started with, the derivative of this product is equal to x e to the 2x. The second part of the problem asks us to find the equation of the curve. It says hence or otherwise, but usually when it says hence or otherwise it means hence, and if you've come up with another way of solving it, good on you, but this is probably the way to go about it. So what do we know? We know that the derivative of this thing is equal to this. That means that the integral, if we integrate both sides, the left-hand side will just lose its derivative, and the right-hand side will gain an integral. And that is how we've managed to get the y on its own. Remembering that the question says find y, find the equation of the curve. So we just need to find this integral here. We can't cancel e to the 2x on both sides if you're thinking that, because one of them is trapped inside an integral. But we can find the integral of this right-hand side by doing integration by parts again. And it did say, it was sneaky, but it said you may use integration by parts in this question. It meant both parts you could use it. So if we call this f and this g dash, think about why I chose it to be that way and not the other. Remember, we want that right integral to be easier, and f dash is 1. If we did it the other way around, f dash, we wouldn't get any easier, we'd actually get worse. So it's integral of f, the integral of this is f times g. Looking at the integration by parts formula, right? The first thing in the formula is f times g. Well, f is just x, and g is the antiderivative of e to the 2x, e to the 2x over 2, minus the integral of f dash g. So f dash is 1 and g is e to the 2x over 2. I'm going to integrate that. Now, one thing to note is when you use integration by parts, when you find the g part from the g dash, you don't need a plus c. You just need the plus c when you do the last integral. So we've got e to the 2xy equals x e to the 2x all over 2 minus the antiderivative of e to the 2x over 2, which of course is e to the 2x over 4. So we get another division by 2, and we've got a plus c there. If we don't put the plus c in there, and I forget about it till the very last step, I'm going to have the wrong answer to the question, because I now need to make y the subject, and I'm going to divide everything through by e to the 2x. So this is where I do the division. E to the 2x cancels there, 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 and I get over e to the 2x. And if I didn't put the c there, I wouldn't get this extra function c over e to the 2x. So I've got x over 2 minus a quarter plus c over e to the 2x. And then the last thing is to find the c. We're told that the point passes through, the curve passes through the point 1, 1. So when x equals 1, y is equal to 1. So we have 1 equals a half minus a quarter plus c over e squared. If I rearrange this equation, 1 take away a half plus a quarter times by e squared, I get 3/4 e squared. So my curve y equals f of x is equal to x over 2 minus a quarter plus 3/4 e squared over e to the 2x, which could be written as e to the 2 minus 2x if you wanted to, but not essential. Cool. Not too bad, but you had to find the connection between the two problems. You had to realise that with the first proof, which was actually fairly reasonable, it's just product rule, that we could use that in the second to start it off, and that integration by parts was going to be useful to us. Anyone who does Cambridge maths would have seen integrals like that before, and you've probably used this thing called integrating factors. If you haven't done that because you're an NCA student, look up the method of integrating factors, because that's essentially what we did there, except that the first part gave us the hint, which if you used integrating factors you would need to know how to do it without the hint. Okay, catch you in the next video.